Okay, so the idea today is we're going to talk about optimizing under constraints and convex programming, so optimizing convex functions, minimizing convex functions. And partly what I want to do is this is a big topic. And there are whole courses devoted to convex optimization. And it can be quite important in certain areas of statistics, in particular for working on high-dimensional statistical problems. But what I hope to do today is just give you a sense for sort of a bit of what this discipline is, and see some sort of common themes of ways that people tackle constraints and working with these kinds of problems. And we'll see that there are going to be some connections with some of the, we're going to see some use of some of the linear algebra things that we've seen a couple units ago. Okay, so first off, in terms of dealing with constraints, so we're going to be talking about both equality constraints and inequality constraints. So we might have things that look like this. So this is a set of linear constraints. Or it might have linear, but also in particular equality constraints. And this is some set of inequality constraints. And so there are going to be a few different ways that we think about dealing with these problems. So one of them is basically reparameterizing the problem. So you guys are already seeing this in terms of if we optimize with respect to a variance or a correlation parameter, that can't be negative, and so we could work in the log of the parameter instead of with the original parameter, and then just do an unconstrained optimization. So sometimes it's fairly easy to reparameterize the problem so that we can get out of having to deal with the constraints. So that's one example. One way in which you deal with these things. We're also going to see the use of Lagrange multipliers, which a number of you have probably seen before. So as usual, I sort of forget when some of these topics have come up. But how many people are familiar with Lagrange multipliers? Okay, so at least some of you. And then in terms of dealing with inequality constraints, what we're basically going to see is that if you have an inequality constraint, basically suppose you can only be in this part of the space, and this part of the space is not allowed, then we're going to see some techniques that basically sort of keep us away from the boundary here in terms of doing the optimization, and that's going to make the problem be somewhat harder, somewhat easier. And then we sort of relax the pushing us away from the boundary and relax that and allow us to get closer and closer to the boundary. So we're going to see some of those different ideas in action today. Okay, so the basic definition of convex programming is we're minimizing some function f subject to some inequality constraints like this, some set m of these constraints, and some set of these equality constraints. And depending on whose notation you see, you'll see this problem sort of written in different ways, depending on whether you use less than or equal and greater than or equal, whether you have the bi on one side or you subtract and put it on the other. But they're all basically sort of writing out the same problem. And it's a convex programming problem or a convex optimization problem if f is convex and if these constraint functions are convex. And functions like this that are linear are both convex and concave, so that satisfies the conditions there. And then I'll note that you can convert this to other forms, like if you wanted greater than or equal to, then you can just take minus hj of x. And if you wanted to get g of x equals to b, so in a nonlinear equality constraint, then you could replace, you could use two constraints greater than or equal to and less than or equal to that look like this form as well. So basically you can sort of manipulate things in general to get them into the form needed for the particular notation that's being considered. And then another definition or terminology here is that if we have some vector x that we're thinking might solve this problem, might solve this optimization problem, it's said to be feasible, the vector x is feasible, if the constraints are satisfied for x. So we can only consider vectors x that are feasible because those are the only ones, sort of a tautology here, those are the only ones that satisfy these constraints here, and therefore those are the only ones that we're going to consider. So if you are able to identify that you have a convex programming problem, and there are lots of sort of standard statistical and machine learning optimization problems that people have determined are convex programming problems, then there is good technology for solving these problems, even with hundreds or thousands of variables. So if you can at least recognize that, then you can sort of go, and that opens up this wide body of knowledge and technology that people use. And then the other thing I'll mention here is all of these terms like linear programming, quadratic programming, second-order Kuhn programming, semi-definite programming are all basically special cases of convex programming. So if you hear those terms, that's basically it's basically talking about a particular kind of convex programming. Okay, so let's talk about a few examples. So the simplest case of convex programming is called linear programming, and that's basically I want to find an x to minimize this linear function as a function of x with respect where I satisfy this set of inequality constraints. Okay. So another little bit of notation is that this little this set of notation here is basically the same as I could say AI transpose x. I can collect that all into a matrix A times x. And so that's basically the AX, this little less than or equal to B, is basically just saying A1 transpose X less than or equal to B1, A2 transpose X less than or equal to B2, and so on and so forth. And this notation just means that whole collection of inequalities here. Okay, so in terms of solving a linear program, and it's because of the fact that this is a fairly simple situation, it's not too hard to deal with or to sort of see what's going on. So if we think about, I'm going to do this in 2 dimensions. So suppose we're trying to minimize with respect to x1 and x2. Well, I have a linear function, so this is just going to define a plane in this space. So this is some plane. I have some contours of that plane. And let's suppose this is the downhill direction. Well, in general, if I didn't have the constraints, I would just keep walking downhill and there wouldn't be a minimum. But if the constraints are such that I have a minimum, then what it's going to look like is each of these inequalities is going to basically give me a hyperplane that basically demarcates the space, and I have to be on one side of that hyperplane. So in general, so in this picture, the way it would look is you would end up having something maybe that looks like this, and each one of these lines is one of these conditions. So maybe this one is the A1 transpose X less than or equal to B1, and this one is the A2 transpose X less than or equal to B2, and so on and so forth. And so the idea of finding the solution X is if I start with a point, basically, if you think about the geometry of the problem, you know you're just sort of traveling downhill on this plane that is giving us, that would be going towards the minimum. And basically, the solution is just going to be at the vertex of where one of these hyperplanes, the appropriate hyperplanes meet. And so the basic way that one way to solve this linear programming problem is basically to start on a boundary and then basically move along the boundary and then keep moving until you get to the vertex that gives you the minimum. So that's sort of the basic story for this linear programming problem. So I don't want to say too much more about that, but just to give you a sense of sort of what is linear programming and sort of what's sort of the basic one basic method by which you can solve one of these linear programs. Okay, so that's sort of the simplest problem. Now we're going to talk about one that's slightly more complicated, and we're sort of going to try and cover a few of these different cases of different problems. Okay, so now suppose that instead of a linear function, we have some general objective function f of x. And I still have a set of these equality constraints. Well, the idea here is I can actually manipulate this into an unconstrained problem. I can sort of reparameterize into an unconstrained problem. So that's another one of these themes in this area is this idea of reparameterization. So let's suppose that x is, suppose x has dimension p, and suppose I have m constraints. Okay, so basically what this amounts to is saying that I only have basically sort of p minus m real degrees of freedom in which to optimize, because I have x, I have an x dimensional, I have a p-dimensional space, but then I have m constraints that are imposed on that. So I'm working in a lower dimensional space in which I have to do the optimization. So the idea is to try and reparameterize so that I can optimize in an unconstrained space that has dimension p minus m. So that's the goal here. So the basic way that we can do this is, again, it goes back to this idea of having a feasible vector. So suppose I have some vector that's a candidate, so a vector x c such that axc equals b. So this satisfies the constraint. So that's at least a plausible vector that might represent the optimum value for x. Well, then the idea is if I take, let's see, then I basically want to, well, let me define this. So the null space of this matrix A is the set of points x such that ax equals 0. So if I were to take my xc and add some vector that is in this null space, let me call that w, then if I take a times this, I'm going to get axc is just b plus aw, this is 0, so this is still b. So if I start with this and add the w that satisfies this condition, then the result is still going to be in the set of feasible candidate points x that could be the minimum. So then the question is, well, how do I reparameterize in terms of w? So the idea is I'm going to that I want to, let's see, what am I here? I'm going to reparameterize it in terms of bz, and so the basic idea here is I have some candidate xc, and I know that that any feasible x is going to be my original sort of starting point or candidate point xc plus bz for any unconstrained vector, any z basically. So the idea is I reparameterize such that b is going to be basically a set of basis functions that parameterize this thing called the null space of A. So how can I do that? Well, so if I can do that, I've basically rewritten the problem as I want to optimize with respect to x, but I start with my xc, and now I'm going to optimize with respect to z. So I'm going to rewrite the objective function as h of z is f of x sub c plus b of z. Well, this z is going to be in this p minus m dimensional space. So instead of optimizing my original f, I'm now going to optimize this h of z with respect to z, and that's going to be an unconstrained optimization problem. So I've done a reparameterization. So then I can go ahead, I can think about writing out the gradient of h, and I can take derivatives, I can take second derivatives, write out what the Hessian of h is, and that's going to be a function of the Hessian of f, and the gradient is going to be a function of the gradient of f by. So let's see, what else do I want to say here? So one way that you can get b, basically this reparameterization, is you could work with the SVD. So if you write A is equal to U D B transpose, and then if we think about taking A times BZ, what I want to be the case is that A times BZ, which is this A times W here, is going to be equal to 0. And if I write out A as U D B transpose, and if B is the columns of V that correspond to the singular values, the values in D that are 0, then basically B amounts to a set of columns. And it's not too hard to see that if you sort of work through it and think about multiplying columns times rows of V transpose, that this is going to work out, that this is going to be, that basically this is going to cancel out and give us back 0. So we're basically sort of taking this p-dimensional space And we're splitting it up into the space that corresponds to the constraints and the space that corresponds to this null space. That is sort of the space in which we are free to move and is unconstrained. So that's sort of the basic story that we would that would be sort of a basic reparameterization that we could do in this problem. Okay, any questions or comments at this point? Okay, so that was if we had equality constraints, and what that allowed us to do was basically do this reparameterization and monkey around with this null space of A. More generally, we might have more general functions that are not linear. So we might have some gi of x equals to b, and those might be the constraints that we're working with. And so if that's the case, then we start getting into dealing with Lagrange multipliers. So the basic story is that we're going to have our Lagrangian function that instead of just having f of x, we're going to expand it to be this function of lambda and x. So we're going to have the original function that we want to optimize. And then I'm going to have some vector lambda times g of x, where here g is going to be a vector. So this is all of the set of these constraint functions that I have written up here with their corresponding b's. So b is also a vector. And now the idea is that if I do take the derivative with respect to lambda, well, this is just linear. And if I take the derivative with respect to lambda, then the derivative of this L with respect to lambda is going to be equal to g of x minus b equals to 0. So that's going to give us that this g of x equals b. So it's basically a trick, that many of you have seen before, to basically ensure that we're not only optimizing with respect to f, but also that we're preserving that we're respecting the constraints that are in the problem. Okay, so that's the motivation for why writing out this new objective function is what we want to do, because if we take the derivative, then we get back the constraint that we're trying to satisfy. So then just to give an example of then how would you go about solving this, and just to see that this sort of relates back to other kinds of manipulations that we've done before. So here's an example. So suppose we have a least squares problem, and we have some f of x, and it's quadratic in x. So I've just written it out as a quadratic function. And then I have a set of in this case, equality constraints, just for this example. Then I can write out the equality constraints in terms of the Lagrange multiplier. So then I get this new objective function. And then if I take derivatives with respect to x, so the usual story, I'm trying to find the gradient and set that equal to 0. And I'm also differentiating with respect to the Lagrange multiplier parameters. Well, then this gives me the constraint. This gives me basically what amounts to setting the gradient equal to 0 plus a little added piece from the Lagrange multiplier. And now I can rewrite that basically as a system of equations that I need to solve. So I can write that as Q A transpose A 0 times lambda x, x lambda. And that's going to be equal to minus m. Okay, so this is just rewriting that set of equations in terms of a matrix vector problem. So this is just, this just goes back to what we saw in the linear algebra unit. We need to solve a system of equations. So I can just, to try and find the x and lambda, well, I just am solving this system of equations, which if I wrote it out as an inverse would be the inverse of this times this. But as we've talked about many times, the way we would actually do it is we would do a matrix decomposition to solve the system of equations. Okay, so then you would get a solution that looks like this, and if you sort of monkey around with inverses of matrices that have blocks like this, you can actually write this out in terms of inverses, in terms of the inverse of Q, and then some other quantities here. So I think the main point of that was just to point out that what you guys have seen in terms of Lagrange multipliers comes up in these contexts as well, and that as you work your way through, you can end up with basically with the kinds of systems of equations that we've seen before in the linear algebra unit. Okay, so next thing I want to talk about is this idea of duality. And actually, let me say, I forgot I had a picture for the previous problem that I wanted to show that might give a little bit of intuition. If we go back to so if we think about the quadratic problem, then one way to think about what we're doing is suppose we're trying to minimize a function that looks like this, but we have some constraint. So basically, this is some constraint we're trying to minimize with respect to x1, say x1 and x2 here. And this idea that we've seen of reparameterizing basically amounts to saying that this is going to be that function h of xc plus bz. And so basically, sorry, it was f. So basically, by changing z, I'm basically moving along this line here. And so I'm going to minimize just by walking along the line instead of minimizing in the full space. And so instead of having to deal with the constraint, I basically reparameterize so that I'm now working in this lower dimensional space with respect to rather than the higher dimensional space that I started with here. So that's sort of a picture that sometimes helps me as I'm trying to sort of think about what's happening in these problems. Okay, so there's a whole, I'm going to talk very briefly about this idea of duality, and so that's not because it's not important, but just because it's sort of it and these conditions for dealing with constrained optimization are sort of a whole. It would take more time to go through in detail than we have time or sort of scope in the class for. But I just want to give you guys a feel for and sort of have you guys hear some of these terms. So basically, sometimes you can reformulate an optimization problem in such a way that it's called solving the dual problem instead of the original what's called the primal problem. So suppose we have our minimization. We want to minimize some f of x, and we have some constraints written out more or less in the way that we've seen before, as in terms of equality constraints and inequality constraints. Okay, so we can write out a Lagrangian function. So this relates, back to what we were just talking about in terms of Lagrangians, as our original function plus a Lagrangian term in terms of the equality constraints and a Lagrangian term in terms of the inequality constraints. And there's something called the Lagrange dual function, which is basically, if we were trying to optimize this, well, we're trying to minimize with respect to with respect to x. So we could think about minimizing that Lagrangian with respect to x, and that's basically, we talked about profiling when we were talking about optimizing likelihood functions, and we talked about, well, okay, we might be able to get rid of one dimension by finding the minimum in that direction, in that dimension, and that'll give us a lower dimensional problem. So that's sort of what's going on here. We're sort of minimizing with respect to x. And then there's a whole body of work that's been done that basically shows that, so suppose I've got x, and then I just want to do this in 2 dimensions. So this is sort of the lambda mu part of the space, but suppose this were just 1-dimensional. Well, then basically by minimizing with respect to x, I'm basically saying for any pair or combination of lambda and mu, I'm finding the minimum here with respect to x. So maybe that's this point here, and then this point here, and then this point here, and then this point here. So that's going to trace out some lower dimensional, we're going to be in some lower dimensional space after we've done that minimization. And then there's a body of work that says that the resulting function, which is this d of lambda and mu, that function is basically that you want to have mu be bigger than or equal to 0. That has to do with whether or not for the inequality constraints, you're right at the boundary for the inequality constraint, or you're in the sort of freer part of the space. So if you've got some constraint that says you have to be less than or equal to, say, this line, the mu basically amounts to, am I right butting up against the line, or am I sort of in the interior part of with respect to the constraint? Okay, so basically what happens is the dual problem amounts to maximizing this subject to mu being bigger than or equal to 0. This is a vector, so this is this generalized inequality notation that I mentioned before. So it turns out that you can show that this is actually a convex optimization problem because this d is concave. So you could think about either maximizing with respect to that or minimizing with respect to the negative of that. And there are conditions under which, if you've rewritten it this way, and if you maximize this, so that's this d of lambda and mu is, so I'm going to have some, let's see, how do I want to write this? So for any pair lambda and mu, I'm going to have some x star of lambda and mu. And if I, under certain conditions, what happens is you can basically maximize this d of lambda and mu with respect to lambda and mu. You're going to get lambda star and mu star when you do that maximization, and then you can plug those back in and find the x star that is, and if if certain conditions are satisfied, that is the solution to the original optimization problem in terms of the x that you're looking for. So basically, whether or not solving this dual problem of maximizing this is equivalent to finding the minimum for x amounts to whether or not there is this thing called the duality gap or not. And so if certain conditions are satisfied, these things are called constraint qualifications, then there's said to be no duality gap, and then you can solve that dual problem. That's going to allow you to solve the original problem that you're interested in solving. And in general, in many cases with convex programming, this will be the case, that there will be this dual problem that you can solve instead of the primal problem. Okay, so that, I know that was sort of quite abstract and not very detailed, but I just want to sort of give you a sense of sort of, if you hear these terms of having a dual problem or a duality gap, sort of what they amount to. And they basically amount to thinking about this Lagrangian, which relates to things that you've seen before and are more familiar, and then knowing whether or not you can solve it by basically carrying out this set of operations here, and basically rewriting the problem. Okay, so I have an example down here for a very simple problem of what this set of operations would amount to, of doing this minimization with respect to x, and then doing the maximization with respect to lambda and mu, although in this particular case all I have is lambda. And I don't think I'll take the time to go through that, but you guys can look at that on your own. Okay, and then the other aspect of this that goes along with this issue of the dual problem is what are called the Karush-Kuhn-Tucker conditions. So this basically gives you conditions under which you can be assured that you have a solution, a minimum for a constrained optimization problem, and basically gives you conditions for if you have some candidate x. For whether or not that is actually a minimum. So if we remember back to sort of the simpler kinds of problems that we thought about and that you guys have seen, even before this class, if we're taking a derivative and then a second derivative, we know that the condition is that we want the derivative to be equal to 0 and we want the second derivative to be greater than 0. And if we're in higher dimensions, we want the Hessian to be positive definite. And that tells us that we're at a minimum, and any direction that we go is going to be uphill. Okay. So these conditions, and again, we don't really have the time to go into them into a lot of detail. These conditions are basically a generalization of that simple condition on the Hessian or the second derivative and on the gradient in the constrained optimization problem. So we have the Lagrangian, again, that tries to deal with both the minimization and incorporating the constraints into the minimization. And so it turns out that for non-convex problems, if you have a set of if you have a candidate x star and corresponding lambda star and mu star that are these primal and dual points, and if there isn't any duality gap, then these conditions will hold. And if you have a convex problem, and if these conditions hold, then that tells you that x star is your optimal point, and that these are the optimal values in the dual form of the problem. And indeed also that that this duality gap doesn't exist. So these conditions basically, this is just sort of in some ways just a rewriting of what we have when we have a Lagrange multiplier kind of problem, which is we take the original Lagrangian, take derivatives with respect to x and set that equal to 0, and that obviously we want that because we want the gradient to be equal to 0. And then these basically amount to, well, this is just sort of rewriting what those conditions were, just the inequality, the constraints, the inequality constraints and the equality constraints. And then the mu values here and these two conditions sort of go back to that, what I was talking about with the dual problem. And basically what they amount to is they basically sort of amount to saying either you're on the boundary with respect to the inequality constraints or you're in the interior of with respect to the inequality constraints. And so if you so either you have mu bigger than 0, so mu sub j bigger than 0, and hj of x equal to 0. So in order to have this to equal to 0, I could have this be the situation, or I could have, so that'll be sort of situation 1, or I could have situation 2, which is mu sub j equals to 0. And this condition basically amounts to you being right on that boundary. And so when that's the case, then that inequality constraint is said to be active. And this condition basically amounts to you're sort of in the interior with respect to that inequality constraint. So again, if this were the constraint represented as a plane, if you're on the line, then the condition is said to be active, and if you're somewhere in here, then the constraint is said to be active, and if you're in here, then the constraint is said to be inactive. And so these two equations basically correspond to these two situations relating to that. Okay, so I don't find that all that intuitive, and there's sort of another way of looking at it that I'll say a few words about, which is that if you do have a Hessian matrix, if you do have second derivatives, then we can sort of think about this in what I think is a bit more of an intuitive way, which is, suppose you are at a point x star, which you're claiming is the minimum. Well, then you can think about the conditions that guarantee that is actually a minimum in a different way. So first of all, we can think about taking the gradient with respect to g, which are the equality constraints. So if I take the gradient with respect to g, and if the transpose out with respect to some w is 0, that's what's called a tangent direction. And basically, what that amounts to is saying that if I go in the direction indicated by the vector w, then basically I'm not changing the value of g of x. So that's a direction in which I can move and still have the constraint be satisfied. So in terms of staying in the set of points that are legitimate that could be solutions to my minimization problem. The only directions that I can think about moving are the directions that are these tangent directions, because those are the only directions where if I move in that direction, I'm going to keep this constraint g of x, this particular gi constraint g of x star equal to 0. Or I'm going to, if I have this point and then I were to move away from that point, I can only move in that direction w in order to keep that inequality constraint satisfied. So basically, we can say that we have a minimum if this gradient with respect to x, the gradient of the Lagrangian with respect to x is equal to 0, and if this condition is satisfied for any vectors w such that I've got this movement in the tangent direction for the original equality constraints and for any active inequality constraints, which are the constraints where I'm basically right on the constraint line. So basically, these are the constraints that are basically amount to equality constraints if I'm sitting right on that inequality on that boundary. So the basic idea here is these directions w are the directions that I'm allowed to move and still have the constraints be satisfied. So those are the only directions I can move. And the idea is that I have a minimum if in any of those directions, if I move away from x star, I'm moving uphill. So it's basically just sort of a reworking of the problem. And so in the usual unconstrained optimization problem, if we're at a point that might be a minimum, then if the Hessian is positive definite, I know that I'm at the minimum. Well, this is just basically restating that in this form to say, if I'm at a point that's a minimum, I only need to consider the directions, moving in the directions that will still satisfy the constraints. And then if the Hessian if the Hessian sort of in those directions tells me that I'm moving uphill, then I know that I'm at a minimum. So that's sort of the basic idea here of what I see as sort of maybe a slightly more intuitive way of thinking about these conditions for finding a minimum, is that instead of the general case of wanting the Hessian to be positive definite, I need to have the Hessian be positive definite, but only in terms of moving in certain directions, where the directions are the directions that it's actually possible to move in and still have the constraints be satisfied. Okay, so that was a very, very brief, just sort of getting your toes wet mention of some of the things that come up when dealing with constrained optimization. So I want to mention sort of one standard method for solving convex optimization. This starts to get towards sort of a more practical perspective on this, because this relates to some of the methods that are actually implemented for solving these kinds of problems. So the basic idea here is I'm going to start with my optimization problem that has constraints. So suppose I have inequality constraints and equality constraints. And what I want to do is I basically want to get rid of the inequality constraints and turn this into a problem where I'm doing optimization and I only have equality constraints. So the trick is going to be that the problem is that if this is where the constraint is, I'm okay in this part of the space, but I'm not okay in this part of the space. So I don't want to venture over into this part of the space. So the basic idea is I'm going to try and move the inequality constraint into the objective function. So here's the original objective function. And then, sorry, this should just be j. I was trying to change my notation and I left the I in here. So this is going to be an indicator function that's going to be 0 here in the part of the space that's okay for x to y according to the constraint. And then I'm going to set this to be infinity up here. So that's what this indicator function is going to do. So now I'm going to try and optimize with respect to this new objective function. I'm going to try and minimize with respect to the new objective function. So as long as I'm in here, that new component is going to add 0 to the f of x, and I'm just going to be doing my usual minimization. If I'm out here, then that's going to add infinity, and obviously that's not going to be where the minimum lies, because infinity is obviously a big value. Okay, so that's fine as it is. The problem is this is not a smooth function. So any of the sort of methods that we use where we try and take derivatives are not going to work with this with this kind of function. So the idea is to change the problem slightly and replace that indicator function with this new function here. And if you sort of play around with what this looks like, what it basically looks like is it's going to look something like this. So we're trying to sort of approximate this function with this smooth function here. And the idea is that as t gets, let's see, where is it here? So as t gets bigger, so I start out looking something like this with some value of t, and then as t gets bigger, this function sort of more and more closely approximates the original sharp function. So basically I have a sequence of values of t such that this function here looks more and more like that original indicator function, which is basically the problem that I really want to solve. So basically I start with a t that gives me something that looks like this, and I'm going to optimize with respect to that and find the minimum. And that might actually keep me away from where the true minimum is because of the effect of this. So maybe I optimize and I find out that my optimum value is here. Well, then the idea is I'm going to sort of relax the effect of this and let this move closer and closer to this, if indeed the minimum of f of x is closer and closer to this point here. So I set up basically an iterative algorithm where first I solve the problem where I use this as my replacement for the inequality constraints. Then I shift up and up. I shift more and more so that I'm using this as my solution to the inequality, as the replacement for the inequality constraint. And then basically this is going to then converge to the actual optimum. Okay, so I've got my objective function, I have my inequality constraints, and I have my equality constraints. I've basically taken my inequality constraints and moved them into the objective function. But I still have the equality constraints that I need to satisfy. So then the question is, well, how do I satisfy the equality constraints? And basically we're going to use Newton's method or a Newton-like method where we incorporate the equality constraints. So the basic idea here is as follows. And again, sort of going back to another theme that we already saw, suppose I have some point xt for which f prime of xt equals, a point xt, and it satisfies the constraints. So a xt equals b. Well, then when I take my next step in Newton's method, what I want to have is that f prime of xt plus my step delta is equal to 0. So basically I'm doing a minimization with respect to delta, so I'm trying to figure out where to move to. And I also want that a times delta equals 0, so that I have a times my new point is going to be xt plus 1. So that's xt plus delta. And if a delta is 0 and a xt equals b, then my new a times xt plus 1 is also going to be equal to b. So the equality constraint is still going to be preserved. So basically Newton's method with equality constraints amounts to taking my Lagrangian, and I'm going to write this out as a Taylor approximation. So f of xt plus, for some small delta ft times the gradient of f of xt plus, sorry, I'm running out of space here. Okay, so that's the that's my Lagrangian, where I take my f of x and I do a Taylor approximation to approximate it. So I'm basically trying to convert the problem into basically, I now have a quadratic function here in delta. And then this term is supposed to ensure that I'm still satisfying the equality constraint. So now what I'm going to do, I'm going to take dl with respect to x, I'm going to take dl with respect to lambda, and I'm going to get that I've got the gradient, I'm taking dl with respect to delta, because I'm trying to find what should be the delta that will give me, that delta is going to give me xt plus 1, since xt plus 1 is just xt plus delta. So okay, so if I take derivatives with respect to delta and with respect to lambda, so again, sort of solving the Lagrange multiplier problem. And now I rewrite this in terms of matrix vector notation. What I get is this is hf of xt, A transpose A 0. So I have a new matrix with blocks in it. This is delta, this is lambda, and this is minus the gradient of f of xt, and this is 0. Okay, so again, this is a system of equations that I can solve by decomposing this matrix, the usual thing that we've seen before. You'll notice this is basically what I already showed you when we saw this example a few subsections ago, where I said, you know, suppose we have this problem here that is a quadratic, minimizing a quadratic function, plus I have my equality constraints. That I can solve that problem, and I can do it in closed form, and I get the answer x and lambda. Well, what I'm trying to show you guys here is that using Newton's method with respect to and including equality constraints is basically solving that problem that we already saw. So what are we doing here? Well, we're basically taking f, which is not quadratic, getting a quadratic approximation to it, and then solving that, doing the minimization in that quadratic approximation. We saw that problem before. In this case, it's embedded in an iterative algorithm where we're solving that quadratic optimization problem with constraints at each of the steps that I'm taking in the iterative algorithm. So that's sort of the basic story here when we're trying to do a Newton-like approach, but have to deal with the constraints. So I will close there. I'll show you a quick example of using an R function constraint optimization next time, and then we'll launch into integration and differentiation.